All right. So we left off on what's today? Thursday, yesterday, talking about acids and how strong acids will dissociate and how weak acids don't dissociate fully. And we also talked about, we didn't get a chance to talk about bases, but let's start there for today. What's today? The 25th. All right. And today I'm just gonna introduce bases, and we're going to talk about some neutralization reactions or reactions that happen when you have strong bases and strong acids. And then we're going to move into redox reactions. All right, so bases, we already talked about in a sense of them accepting H plus, right? And typically a strong base, when it's ionized, it's going to produce hydroxide anions. So when it's ionized in water, right, it's going to produce a hydroxide anion. That's literally the proof of what a base is if when it's ionized in water. Now, that's not a catch-all because there are other types of bases that don't produce hydroxide anion. But if it's in water, it's going to do proton transfer with water and produce a hydroxide anion, right? So an example would be sodium hydroxide, and we're going to add water to that. And in this case, this is going to be my base. This is my acid, right? And when that ionizes, because it's a strong base, and what I mean by ionize is that remember, this is a salt, right? So it's made up of Na plus and then OH minus, right? So it has a cation and an anion, right? So when that ionizes, right, you're going to get water plus Na plus OH minus, right? So all of your hydroxide salts are strong bases. Right? So these are all strong bases. And so when you think about um, what a weak base is compared to a strong base, right? They do not ionize. They still produce the hydroxide anion in the product, but they don't ionize, right? They only partially dissociate. Right? So we take something like ammonia, which has a long pair of electrons, and I'm talking about this from the perspective of the electrons, because at some point we're going to move away from like just saying things happen to showing how they happen. Right? So that's why I'm kind of introducing you to the curved arrows and things like that. So if I dissolve up ammonia in water, this is going to happen where it does proton transfer. This is the base. It's a weak base. Really, in organic is not as weak as as some of the other bases. It's actually a pretty decent base. But this is the base, and then this is the acid in this case. And the equilibrium is going to lie to the reactant side, because if it's a weak base, it's not going to fully dissociate. And I have a graphic I want to show you before we move on to talking about these neutralization reactions. Right, so this is going to be a conjugate acid. And this is the conjugate base. Remember, the conjugate acid is the base after it picks up H plus. The conjugate base is the acid after it loses H plus. All right. So let me show you real quick if I can get this to work. I'm going to actually open up the book. I had the website open already, but ended up closing down the internet. Let me go and find it, because I want to show you this whole dissociation. I want you to see it visually. So give me 1 second. Let me find the book right quick. Come on, book. Let me reshare. So this is a section on acids and bases is actually a really good section, but let me just pull up the right here. What this looks like and how to think about this on a micro level. All right, so you can see right here, if it's a strong acid, excuse me, if it's a strong acid like this, can y'all see my screen where it says HA?
Yes, sir.
So I got HA, that's my acid, and this is water. So I'm adding the acid to water to dilute it up. And again, in this case, if I'm adding acid, the water is acting as a base. So the water is going to do proton transfer. So this H that's here, this little small sphere, that's going to get transferred to water and it's going to become hydronium, right? And then the A minus is the conjugate base. It's the acid after it gives up H plus, it becomes the conjugate base, which is here. Now, if you look on the micro level, you see a whole bunch of A floating around in here, right? You also see a whole bunch of H3O plus floating around in here. And what that literally means is that this acid fully dissociates. It gives all of its H's to water to become H3O plus, and conjugate base is here. So you see, that's what you see in solution, a total dissociation. Now I want you to notice something else too. If I put the pH meter down here, the pH is 2, right? How many of you remember pH from high school? And what the pH scale, what the numbers mean on that scale? Anybody? Is it okay? So the scale is from 0 to 14. 7 is neutral, 6 and below is acidic, and 8 and above is basic. So a pH of 2 is a very, very acidic solution, right? That's a strong acid. But if we do a weak acid, look at the pH difference, right? So pH is 4.5. That means that there's a lot less hydrogen ions in solution. That's what the pH means. We're not going to go into great detail about that. But then over here, if you look at what's happening, so this is my acid. This is a weak acid. This is my acid. This is water. And when this acid gives up H plus to water, that becomes H3O plus. And then the it becomes the conjugate base, right? But look in the solution. You got a lot of acid still intact. A few acid molecules have given up H plus, and you can see the conjugate base, and you can see the H3O plus. But for the most part, this solution is mostly acid. And that's because weak acids don't readily dissociate. So with this equilibrium right here, which way do you think the arrow is going to be pointing? Because if I'm going to the right, that means this should be disappearing. The HA should be disappearing. But if you look here, it's not. So which way do you think the equilibrium arrow, like if I ask you to draw the or indicate which direction equilibrium favor, what would you say based on this?
Would it be going to the left?
Going to the left, right? This is not dissociating. And so the forward path is very slow, but the reverse path, right, is let me not say slow. The forward path doesn't happen as much as it would if the acid was stronger, right? So you're going to have a bunch of this left over. You're going to have not very much of this being formed. So the reactants are going to be favored in this case, right? And it's the same thing for strong bases. You see how this is the base. You have some metal and a hydroxide anion, preferably a group 1 metal, because we know that hydroxide is not soluble with a bunch of other metals except for barium. So we look here, you can see the metal, which ends up being the orange atom or the orange ion. And then the hydroxide group, which is here, OH, you can see that's fully dissociated. When this is in water, it's fully dissociated. And the pH is 12. That means it's very basic. Anything 8 and higher is basic. So 12 is almost to the maximum pH for a base, which is 14. All right. And then a weak base is not going to dissociate very much, and it's not going to do much. And notice the weak base, when we talk about dissociation, is not really dissociating as much as it's doing proton transfer, right? If you look at the strong base, you can see it's a salt. So when you put that in water, it's going to dissociate. But when you have a weak base, it's not always a salt. Sometimes it's an organic molecule like ammonia, and there's no dissociation, right? So you look here, you have a bunch of this left, a lot of it. Then you have a few OH minus molecules from proton transfer with water, but not much. All right, so I just wanted to illustrate that and use that, kind of to give you a visual representation of what it looks like to say that some acid is weak or a base is weak, right? If it's a weak base, it's not going to do proton transfer as readily with water. And so you're going to get a little bit of this conjugate acid and a little bit of the OH as the conjugate base, but not as much. If it's a strong base and it's a salt, it's going to fully dissociate. Yeah. Same for weak acids. There's not much proton transfer happening here. So you see more acid than you see anything else. And then for a strong acid, it's all proton transfer. So everything every proton gets given away to the water in this case, and then you get a full dissociation. All right, so let me go back to my iPad. And we're going to introduce neutralization reactions. All right. So this is a type of acid-base reaction, because we talked about precipitation reactions so far, and then we talked about acid-base reactions. Well, now we're talking about acid-base reactions. And then we're going to also talk about redox reactions. We're going to introduce it today, but we may not finish it. So neutralization reactions are acid-base reactions where you have a strong acid. And I'm sure you remember this from high school, and a strong base. And those two things react to give you a salt plus water. Right? So let me give you an example here. So let's take barium hydroxide. And HCl. And if we think about this like a double displacement, what products are we going to get? This should be clicking a little bit more now. How to predict these products. Right, if we write this out, this is Ba2 plus, 2OH minus, and then this is H plus the Cl minus. What do you think? If we think of it as a double displacement, what two products are we going to get? Right, is barium going to pair up with the chloride ion? All right, so this is your base. This is the acid. Right, this is my salt and water. Is this balanced?
That's not balanced, right? Because it's missing a O on the right side.
Okay, so we got H2O. I'm going to address your question in 1 second, Mary. Let's do our inventory. We got barium. We got 1 barium. We have 3 hydrogens. We have 1 O and 1 Cl. And on this side, we have 1 barium. We have 2 H's, 1 O, and 2 Cls. All right. So what do you want to balance first? You want to balance the hydrogens, or do you want to balance the chlorines?
Maybe the chlorines.
How are you going to balance it? I'm with you.
Put a 2 in front of that HCl.
All right, let's do that. Let's do that. Let's put a 2 here. And then that's going to change the math, right? So this 3 was actually the way we wrote it. We wrote it as 3 hydrogens, but it's really the 2 from here and 1 from here. So that was 2 plus 1. But now when we put the 2 there, we can say that it is 2 plus 2. So now we're going to have 4 hydrogens. Good. All right. So we got, and then at the same time, we've also balanced the chlorines as well. All right. So now we have 4 hydrogens to 2 hydrogens. On the other side, we have 2 chlorines, which is balanced. So that's balanced. The bariums are balanced, and oxygens are not balanced. Actually, I messed up because this should be a 2 right here. Right, because that subscript is going to be distributed. So that's 2 and that's 2. All right, so we got 2 oxygen. So we need to balance now. We could balance the hydrogens and the oxygens at the same time, couldn't we? Because they're both in the same molecule. They're both a part of the H2O molecule. Let me erase that and just move this up. All right. So if I want to balance those hydrogens, if I put a 2 here, would that get me straight? That's going to be what, times 2. So that's going to be 4. And then that oxygen is also going to be times 2. So that's going to be 2. Now is everything balanced?
Yes, sir.
It is. So all right, so now everything is balanced. So oxygen is balanced, hydrogen is balanced. Right. So now we're good. So now let me address a question that was in the chat about double displacement. So whenever we take 2 salts or 2 ionic compounds, even though HCl is, well, it's mostly ionic, it's almost ionic. It's a weakly covalent compound, but we can still think about it like an ionic compound. So if we take that and we think about the barium, that's barium 2 plus, and this is OH minus, right? That's what that looks like in ionic form. And then we think about the HCl, which is H plus and Cl minus. When we talk about doing a double displacement, what we're doing is taking the 2 cations and swapping them, right? They're going to swap places. So the H is going to come here. Pick a different color. H is going to come here. And then the barium is going to come here where the H is. That's what double displacement is in a nutshell. Just swap cations, and what you get out in this particular case would be barium right, and you would also get out that water molecule. So H OH. Is that clear? Does that make sense?
Yes, sir. It makes sense. Thank you.
So all of these ionic, that's why when we've been looking at the first reactions that we were looking at with solubility and things like that, that's why it's important to be able to write out the molecular form of an equation and then write out the ionic form where you show each salt broken up into its ions, so you can actually see what's getting ready to happen, what kind of exchange is going to happen. All right, but for double displacement, it's really just swapping partners. That's all it is. All right. So with that, that being said, we can actually take this equation and write it out in the ionic form. I want to keep doing that, and the net ionic form. So I'm just going to copy. And I'll erase all this other crap. Except for our coefficients, keep those. All right, so we write this out as Ba2 plus OH minus, and then we put the 2 that's here, we'll put it in front of the OH. And then plus 2H plus 2Cl minus. And that's going to go to Ba plus 2Cl minus plus H2O. All right. And then we can cancel our spectators. So water is on this side. And if we join up the 2 OHs with the 2 H pluses, they're going to combine to give me 2 waters anyway. So we can cancel out our spectators, which in this case is just water on both sides. And now we can write, so this is the ionic equation. Now we can write the net ionic equation, which is Ba2 plus 2 Cl minus, because that's what's left up here, going to BaCl2. Right, so all of your acid-base equations and your precipitation equations, we think about them all the same way, which is what salts are involved, what are the ions involved, and what's going to happen when I react them together. All right. Questions about anything with acids and bases? All right. So we got to get in the habit of writing out the ionic and net ionic equations and things like that. But to do that, we got to have a command of your polyatomics, right? Like hydroxide, like phosphate, sulfate, chlorate, perchlorate. You need to know what those are. And you got to also have a command of the charges that are, used for each element or each ion, like barium. We know barium is a group 2 element. So it's going to have a 2+ charge. Chlorine is group 7. So it's going to have a -1 charge. So it's, when we were first started doing nomenclature and putting ions together to make compounds and things like that, the purpose of doing that was to also build a skill of knowing or remembering or recalling the different group numbers and the different charges and things like that. All right, so now let's introduce, we got time, the redox reaction. So this is a third class. So we did solubility, not solubility, precipitation reactions. We talked about those and how to predict them. We talked about acid-base reactions and how to predict those. And now we want to move on to the third type of reaction, and that is the redox reaction. Right? The read part is for reduction, and the ox part is for oxidation. And they're given together like that because one can't happen without the other one, right? You can't have something getting oxidized without something getting reduced, or you can't have something getting reduced without something getting oxidized. So by definition, when we think about the term reduction, right? Reduction is a decrease in the oxidation number or charge, but we also think about this as the gain of electrons. So it's the gain of electrons. We can also think about it as a decrease in oxidation number. Right? So if we have something like have a, let's say we have an ion with a +5 charge. Actually, let's say it's got a +6 charge. And that ion, the charge on that ion changes from +6 to +1. Let's say that, right? This is a reduction. Right, that's a reduction. Now, the question is, how did that reduction happen? Well, if you gain electrons, that means you're gaining negative charge and you're reducing that positive charge, right? How many electrons would it take if the charge on an electron is -1? How many electrons would it take to make that +6 charge go down to +1? If every electron is a -1. Let's see somebody put it in the chat. Okay, if it's 7, then that's going to make that +1 charge actually -1. But if we add 5 electrons, right? So 5 subatomic particles that have a negative charge, that's going to take that down to -1. I mean, +1. Yeah, I got you. Okay, I see you. So yeah, so the way I write this out as a reduction is I say Z6 plus 5 electrons will give me Z +1. All right, so that's how you illustrate that a reduction happened. A reduction is the gain of electrons or a decrease in the oxidation number. You can see the number went from 6 to +1. And the way that happened is that ion gained 5 electrons. This is just a hypothetical situation. All right. By the same token, for oxidation, wrong pen, Russell. All right. Oxidation is the loss of electrons. All right. And the way that we illustrate this, I'm going to take the same generic ion, but I'm going to give it a +3 charge. And if that goes from +3 to +5, we can write it that way. How did I get that charge to go up to +5? How many electrons would I have to give away? Because every electron is -1 in charge. So if I take away 1 electron, that's going to make that charge go up to +4. And if I take away 2 electrons, it's going to make it go up to +5. Are y'all following that? Every electron I take away raises the charge by 1 or increases the charge by 1 if it's positive. If it's a negative charge, it's going to increase by, well, it's the same. It'll go up by 1. All right. So this is what we call oxidation. We increase the charge, we increase the oxidation number, and we did that by losing electrons. So the oxidation number goes up. So this is what we call oxidation. Right? The way we illustrate it is to say Z3 plus goes to Z5 plus 2 electrons. All right. So if you notice on the oxidation side, the electrons are on the right. On the reduction side, the electrons are on the left. That's important because when we write out redox reactions, that there's a specific way you have to write those. And so anytime reduction happens, you're going to be adding electrons. So that's going to be happening on the left side. And then anytime oxidation happens, you're going to be removing electrons, and you show that removal by showing the new ion that you made and the number of electrons that you lost to get to it. All right. Any questions about that? So reduction and oxidation go hand in hand. They happen. You know, if it's a redox reaction, it's going to be happening at the same time, and that's why you have to write redox reactions in a specific way in order to understand which side is getting oxidized, which part is getting reduced, right? So let me push this topic a little bit further, right? And let's think about a reaction, right? We have, let's say we have sodium solid plus chlorine gas, and we're going to react those together to get NaCl, which is also a solid. I was telling the class this morning, this is a reaction that you could do by taking sodium, and I don't know if any of you have ever worked with sodium, but it's like a really soft solid. It's almost like the consistency of butter. So you can kind of shave off a piece of sodium, put it into a flask, seal the flask up, and then pipe in chlorine gas, either with a balloon or some other type of way. And you can get that to form sodium chloride. All right. But the point is that this is a redox reaction. So we can write this. Some redox reactions we write as, we break them down into what we call half reactions. So we write them as half reactions, right? So we're going to take this and split this into two different pieces, right? So and the half reactions, one of them is going to be the oxidation and the other is going to be the reduction. So we're going to say, well, first let's balance this. Is this balanced? That's always the key. If you don't balance the equation, all the numbers, all the calculations, everything is done. It's going to be thrown off. So you got to balance it before you do anything else to it. Oh, no. That the S is the state. I'm sorry. So that's a solid. That's the state of matter. This is, ooh, that G is horrible. This is a gas. And then over here is a solid. Apologize for that. So anytime you see in parentheses like of course, if it's typed, it'll look a lot better than my handwriting. But if you see a small S or a G or L or AQ in parentheses, it's the state. So AQ is aqueous, G in parentheses is gas, S is solid, L is liquid. Right. But if you look at it, it's not balanced because there are two chlorines on the reactant side and there's only one on the product side. So we need to balance that. So let's balance the chlorines. If we put a 2 here. Come on. Right, that's going to balance the chlorines, but it also throws off the sodium. So what do we need to do for sodium? All right. Yes, put a coefficient of 2 in front of sodium. Boom, now it's balanced. All right, now we can write the half reaction, right? So we're going to write this as sodium, something happening to sodium and something happening to chlorine. So let's write it out like this. So we're going to say, so 2Na, which is a solid, going to 2Na plus 2 electrons. right? The reason why we say that it's 2 electrons is because the oxidation number here is 0 by default if there's no charge indicated. So it went from 0 to +1. And since there are 2 sodiums that went to +1, that means each one of them lost an electron, right? So then that's why it's +2 electrons, right? So this step right here is the oxidation part. All right, so that's my oxidation. And now for the other half reaction, we're going to deal with chlorine. So we're going to say Cl2 is going to 2Cl minus, right? So the charge over here is 0 by default. If it's an element, it's 0. We're going to talk about the rules, but we won't have time to talk about them today. So how do I go from 0 to minus 1? What do I need to do? If I want to make something negatively charged, we're talking about oxidation and reduction. Am I adding or subtracting electrons? If electrons are negative and I want the charge to be negative. So I'm going to add 2 electrons, right? Just like I made sodium positive by taking away electrons, I can make chlorine negative by adding electrons. So now do you see the point that I was making earlier about the oxidation side and the reduction side? Uh-oh. That's not what I was trying to do. On the reduction side, the electrons are added on the left. On the oxidation side, they're shown on the right. So that's oxidation. And then by default, this is reduction. So overall, this is what we call a redox reaction. Right. And if we put them back together, what you'll notice also is with the half reactions, the electrons will usually cancel, right? But there's another type of redox reaction that we're going to actually write out where you'll have to balance the electrons so that they'll cancel. But here it's just 2 electrons in each case, so they'll cancel out. But the idea is that the sodium gets oxidized, the chlorine gets reduced. And so with sodium being the atom that's giving away electrons that some other atom can take, then sodium is considered what we call a reducing agent. Because when it gives away electrons, the chlorine that's reacting with it, it's going to take those electrons and get reduced by them. Right. And then by the same token, the chlorine is what we call the oxidizing agent. So whatever electrons sodium gives away, chlorine is going to take them and get reduced. But by the same token, it's helping sodium become oxidized. So chlorine in this case, if it's the acceptor of the electrons, it's going to be the oxidizing agent. And then the sodium is going to be my reducing agent. All right, but that's just one example of a redox reaction. And we're going to look at a couple of other ones. One of them is pretty lengthy, so we're going to spend some time on that, just walking through the steps as far as how to write it, balance it, and all of that. It's going to look like a lot when we're doing it, but we can handle it. All right, any questions? I see something else in the chat. Yeah, I got you. Thank you, Mary. I didn't see that earlier, but thank you. I see it now. And you're right. We want to add an electron. All right. But any questions about anything we talked about today?